Hello everyone, we are at Beyond the Formula. Let's see why the moon do not fall on Earth. So we have a question here. The moon is constantly pulled by Earth's gravity, right? Correct. Moon, the natural satellite of Earth, moon is constantly pulled by Earth's gravity. Then why hasn't it crashed into Earth? Right? So what are the common answer we get to this question? What are the common answers? Some says distance is too large. Distance is too large between what? Earth and moon. Right? Some says gravity is weak. Right? As gravitational force, weakest force is weak. Right? Some says space has almost zero or zero friction, etc., etc. All right, but none of the reasons or none of the answer is correct, right? All the answers are wrong. None of them are correct. So what is the correct answer to this question? Right, let's see. Right, what do we have here? We have Earth. Suppose say this is Earth, E, and this is moon, M, right? And this is the gravitational force, say F of G, right? F of G. Now if gravity pulls the moon towards it, right? To downward force, right? If you see or just imagine like this, if you just draw the moon above the earth, you will get it. Right? If you draw like this, right? Suppose this is earth and this is the moon here, and gravity is pulling here downward with F of G, right? Now if gravity pulls downward, shouldn't the moon fall eventually, right? There is only one force acting downward, so it should fall, right? It should fall on earth, right? Now you see what happens here. The moon is not stationary. The moon here, the moon is not stationary, right? The moon is not stationary. It is moving, or it has a sideways sideways velocity, right? It has sideways velocity in this direction, say v, right? Some say it's terminal velocity, some says it's horizontal velocity, but it has some velocity in sideways, right? So it has, or it means moon here, so it has sideways velocity of some v, right? Say meter per second or kilometer per hour, kilometer per second, doesn't matter what the unit is. Now you see, let's see an experiment. Let's see an experiment named as Newton's cannonball. Named as Newton's cannonball, right? Suppose this is the earth's surface or ground, right? If I throw a ball from here, if I throw a ball with some angle theta, say, with some velocity v, right? Now if v is, suppose say v1, v2 and v3 with all greater than, like this, right? Now if I throw with v1, suppose it will goes like this, right? If it is v1. Now if I throw with v2, it will go like this, right? Keeping the angle same with this v2, right? Now if I use v3, it is v3 here. So what we can observe here is what this range slow cannonball falls nearby right? Faster cannonball falls farther away right? Now even faster. Now what do you see? If I throw the ball with much higher velocity that it keep missing the earth. It goes like this, something like this. If I throw with some velocity v that is much greater, that it keeps missing the earth, right? Now if you see like this, and if I throw the ball from here with this place, now what happens here? It keep missing the earth. It reaches here, it reaches here, it reaches here. It keep missing the earth. It goes this way. It goes like this. It has it vertical or sideways velocity of v, which is very much high. So this is how moon. So the natural satellite is basically a giant cannonball, right? So you see, the moon is actually falling. The moon is trying to fall, or you say actually falling. The moon is actually falling. But earth curves always, or the gravity of earth saves it. Suppose if I say I have a vertical velocity and I have a downward velocity, say v1 or v2, the net will be like this, right? Now in case of earth, I have thrown the ball with some velocity and the gravity is pulling it downwards, so it has a net velocity in this direction. Now this helps the moon or any object to move in orbit. It helps any object or the moon to move in the orbit around the earth. So what happens here? The gravity provides the required centripetal force. The gravity provides the required necessary centripetal force. So what we can conclude here? The gravity is not preventing the orbit, but what it does, it creates the orbit. Correct? So this is how things happen with the moon. Similarly, Same physics is applied on artificial satellites, right, like GPS satellites. Okay, now we have a good question here. Suppose if I say, what if the moon suddenly stopped moving sideways, right? So what happens? Suppose this is earth and this is moon. Now this velocity v goes 0. So it has only what? It has only g, right? The force of gravity. So does it fall on the earth? Would it fall on the earth? Yes, it will. Yes, it will fall. Right? Now another case, what? What if gravity or earth suddenly loses gravity? What happens if earth suddenly loses gravity? So what happens? Suppose this is earth, this is moon having velocity v. Now this g goes 0. Right? So what happens? The moon goes a straight line. The moon goes in a straight line out of Earth's field. Out of Earth's field. Alright? So you see, the moon doesn't stay in orbit because gravity is absent. It stays in orbit because gravity continuously bends its path. So what we can say, it means moon stays in orbit because gravity continuously bends its path, right? The moon is forever falling toward earth and forever missing falling on the earth, right? So that's all. Thanks.